Bismillah ar-Rahman ar-Rahim. If you have any questions in the previous lecture, first of all, you ask your questions, and then we will start our today's lecture. Please, if you have any questions, you can ask questions.
I have a question, but not from the previous lecture. It's
Who
general.
are you? Who are you?
I'm
Please.
Ahmed Muhammad.
Muhammad, your voice is not very clear to me.
Sir, my name is Ahmed Muhammad.
Okay. Please, Ahmad Muhammad. Carry on.
Yes, actually, my question is from chapter 1 of
From?
chapter 1, the book of Design of Reinforced Concrete by Jack McGregor, I think.
Okay. Please ask your question.
So it's actually, I guess I want to know what the effect of the creep in reinforced concrete column that are subjected to axial compression loads.
The effect of creep.
Yes.
The creep is, that a phenomena which occurs at the sustained loading. You know this?
Yeah, the what I know about creep is like it's just like deformations, the second deformation to structure element.
Yeah. At the sustained loading, not the additional loading. Sustained loading means that if load exists for a long time on a reinforced concrete element, then it will deform with time at this sustained load, not additional load. So this is the creep phenomenon.
Okay. And
Now
what is
your question?
to reduce that?
Okay, how can you reduce this? You can reduce this if you prepare good concrete, which have less moisture, which is called high performance concrete, by reducing water cementation, adding some plasticizer in order to achieve good strength. So when pores are less, basically these are the pores in concrete which are compressed with time at sustained loading. So if we can reduce these air gaps and pores in concrete, then creep can be reduced. However, complete elimination of creep is not possible because the structure of concrete is such that the complete elimination of pores will not be possible. However, they can be minimized, and then creep can be minimized. Creep is not detrimental if it is within the limits.
Okay, that means the reduction should be included in the designing time.
Yeah. If it is in reinforced, there are two types of concretes. In reinforced concrete, creep is not a severe problem. It is a problem, but not a problem out of control. However, in pre-stressed concrete, I hope you know pre-stressed concrete. In pre-stressed concrete, creep shall be minimized because creep is then associated with the pre-stressing forces. So if whatever pre-stress force is lost due to creep is basically lost in the capacity of the member. So creep is important in the pre-stress concrete. It must be controlled, or it must be known to us at least before we design our pre-stress members. However, in reinforced concrete, it is not of so significance.
Okay, I understand. The last question is, yes, I want to ask about epoxy coated bars. What are they? And they said also sometimes are used in construction of reinforced concrete.
Epoxy, can you repeat your question?
I said epoxy coated bars.
Epoxy coated. Okay, epoxy coated bars.
Yes.
Epoxy coated bars are used in situation where there is a high probability of corrosion due to exposure of the reinforcing bars. So in seaside where the sulfur dioxide, and other
Yes.
Other detrimental elements or compounds exist in air, and they can take concrete, and thereby they can deteriorate concrete. And once concrete cracks and deteriorates, the steel will be exposed to air, and steel can then get corroded. And other situations where steel is placed in the piles in bridges, for example, deep down the earth. So in these situations, the steel is highly exposed to corrosion. In order to avoid this corrosion, sometimes the steel bars are epoxy coated, and these epoxies are basically corrosion inhibitant. So these corrosion resistant epoxies, they are very smooth in nature, and these smooth, they will increase the smoothness of the bars. So when they increase the smoothness of the bars, they can be pulled out very easily from concrete. So when epoxy coated bars are used, they must be inserted in concrete up to enough length so that they are not pulled out. For this reason, when the bars are epoxy coated, so their embedded length, the requirement on the embedded length increases. And for this reason, the code has differentiated the normal uncoated bars from the epoxy coated bars. If you look at the code requirements for uncoated bars, the requirement on development length and length is less than the epoxy coated bars. Okay.
Yes, sir. That's quite nice. Thank you.
Any other question?
Assalamu alaikum, sir.
Walaikum assalam.
Amir Hamza, sir.
Okay, please ask your question, Hamza.
सर अगर हम फ्रेम स्ट्रक्चर को डिज़ाइन कर ले और उसके जो इनफिल वाल हो उसका लोड बीम पर मतलब एज अ लोड हम अप्लाई करें सर, इनफिल वाल उस पर ना बनाए, तो बाद में सर सिस्मिक इफेक्ट इस पे होगा अगर रियल में फिर वाल इस पर हम बनाए, मतलब उस टाइम डिज़ाइन में हम सिर्फ बस डायरेक्ट लोड ले लेना.
No, yes, I understand your question. You are asking that infill walls, the load of the infill walls is basically resting, is coming on the beam. Okay, we know this. Okay, because most of the time it is not necessary, but most of the time the infill wall will be constructed on the beams, which means on the column center line these walls shall be erected. But as you can see that in reinforced concrete from frame structures, it is not necessary that every wall is supported on beams, because there may be a room size different than your grid size. You know that beams run on the column center lines, and it is not possible to place our walls on every grid line from the requirement of the space and other things. So it is not necessary, and usually it is not possible that all walls are placed on the beams. The walls may be placed somewhere else, which means the wall may be placed on slab directly, which is usually the case. However, your question is that if walls are placed on beams and then the infill walls are encased or enclosed between the frame elements, between the walls, between the beams and the columns. Okay, this is your question. That if an infill wall is enclosed between the frame elements, the vertical elements, columns, and the horizontal elements, beams. So your question is that if this wall load is taken in our models as a load on the wall, instead of modeling this wall in our finite element models. Is that correct?
Yes, sir. Yes, sir. Exactly.
So when this load is taken on the beam, so this is correct, that if the load is taken on the beam, so beam can be designed for this. However, if you do not model your infill walls in your ETABS and SAFE numerical models, then the lateral load, which is resisted in reality up to some extent by these walls, will not be taken into account. And the portion of the reinforced concrete frame structure where these infill walls are situated will be resisting in reality the lateral loads with much stiffer elements than the elements where there are, and then the locations where there are no walls. So on one side there will be stiffer elements, and on the other side there will be flexible elements. So this will cause torsion in the frame, and this torsion is ignored in the models or is not taken into consideration if these infill wall modeling is ignored. So this can create problems, and this is what we have explained in one of our slides, that this can cause horizontal irregularity, and these irregularities must be taken into account. In reality, what happens is that in high-rise buildings, in most of the time, these walls are not coming on the beam column center line. They are widely spread in the on the floor of the reinforced concrete frame structures, so thereby not too much affecting the overall lateral capacity of the structure. However, if they are enclosed within the frame elements, then they will affect the lateral load resisting capacity of the frame elements, and they must be taken into account wherever they exist. And another point is that these walls are provided, but then the walls have openings. The walls are usually not too thick. They are thin walls in order to reduce the load on them. So up to this extent, we can say that if these walls exist in a reinforced concrete frame elements, only transferring their load to the beam will not be sufficient. They must be modeled properly in the numerical models.
Okay, sir. Thank you, sir.
Any other question? Okay. If there are no questions, so let's start today's lecture. In the first topic in today's lecture is a very important topic, which basically compares the gravity loading actions and the earthquake loading actions. In this figure on the left, you can see a frame, which is basically a single bay, single story frame, and this frame is subjected to gravity load. Okay, and you would have analyzed such systems many times in your analysis courses. You know that when this frame is subjected to gravity load, then the stresses will be, the tensile stresses will be produced in the frame like this. You would have tensile stresses at the midspan in the beam on the bottom side of the beam. Bottom and top are important to note. On the bottom side of the beam, because there will be flexural tensile stresses on the bottom side because there is elongation on the bottom side of the beam. So flexural tensile stresses will be induced in the midspan of the beam, and flexural tensile stresses will be produced in the upper part of the beam at the ends of the beam or at the beam column connection. Beam column connection are these points. So within the beam, the tensile stresses due to gravity load will be produced in the bottom of the beam at the midspan. But as we move from midspan towards the end of the beam, the tensile stresses location will change, and the tensile stresses will be then produced in the upper fibers, which are called negative bending moments, and the midspan bending moments are called as positive bending moments. So this is known to you, and this is very clear to you. The bending moment diagram you would have drawn several times. You can draw the bending moment on tension side or compression side. This bending moment has been done on tension side. So you can see that the bending moment diagram is like this. Tensile stresses here on the bending moment at the midspan of the beam, and then we have tensile stresses here at the ends of the beams and the upper side of the beam, and so on. You know these things very well, and you would have drawn several times bending moment diagrams for single bay, single story frames. Now we are going to compare these actions when this frame, the same frame, is being hit by an earthquake. When this frame with the gravity load existing is being hit by an earthquake, the beam will move to the left and right, as shown in this figure. When this frame moves to the right, so this frame is moving to the right. When the frame moves to the right, you can see from the deformed shape of the beam that tensile stresses at one end of the beam on the left end now will be produced in the bottom of the beam, and on the other end of the beam, tensile stresses will be produced on the upper side of the beam. And you can see in the columns also the stresses will be produced. They have been marked red. You can see this. Okay, now when the beam moves to the left, so when the beam moves to the left, these tensile stresses locations are reversed. The reversal of actions take place. So that tensile stresses in the beam will occur at the bottom of the beam. At this end, in the previous case, the tensile stresses were produced in the upper part of the beam here. The tensile stresses are produced in the upper part when the frame moves to the right. When the frame moves to the left, the tensile stresses at the same location will produce in the bottom of the beam. Similarly, at the other end also, the tensile stresses location will reverse, will change from bottom to top. So if we combine now all these three actions, the two actions of the earthquake and one action of the gravity load, because when this frame is being hit by an earthquake, the gravity loads is obviously there. The gravity load is there, and the frame is being hit by an earthquake, thereby producing some more effects. Okay, so now we will combine all these effects together. For example, if this bending moment, you can see the cursor on the right of the beam in the gravity load. You have bending moment, negative bending moment at the top side of the beam on this end. So this bending moment will be added to this bending moment which is coming from the earthquake. These two will be added together. So the net result will be that this frame must be designed for additional tensile stresses. In other words, the bending moment due to earthquake, this bending moment in the figure below, this bending moment which has been produced due to gravity load shall be added to the bending moment produced at this location due to earthquake load, which is this bending moment. So this bending moment must be added to this bending moment. And then the reinforcement at this end must be provided against this combined bending moment. Okay. On the other side of the beam, here the tensile stresses have been produced due to this bending moment. So this bending moment must be added to this bending moment, which is the bending moment produced due to earthquake when the frame moves to the left. And the tensile stresses in the upper fibers of the beam will be produced due to this combined action. So reinforcement must be provided at in the beam at this location for this combined bending moment, which is being produced partly by the gravity load and partly by the earthquake load. Understand? However, if you look at the midspan bending moment in the beam, so at the midspan, the bending moment is there from the gravity load, but there is no midspan bending moment coming from the lateral earthquake load. So the bending moment at the midspan in the beam will remain the same, it will not change. The bending moment in the columns will also change. As you can see that there is a tensile stress here, but this tensile stress will be added to the tensile stress produced due to the earthquake loading here, this location, and at the bottom of the column, this will be added to this. Similar, so all the bending moments will be added together. The bending moments from the gravity load and the bending moments from the lateral load will be, from the earthquake loading will be added together, and then for this combined bending moment, reinforcement will be provided. Okay. What is the conclusion? The conclusion is that if you look at these bending moments, both in beams and columns, the bending moments occur at the ends of the columns and beams. The bending moment due to earthquake loading does not occur at the midspan of the beam or mid height of the column. They do not occur at the mid height of the column or midspan of the beam. So the bending moments, we can conclude from this that the bending moments due to earthquake are produced at the ends of beams and columns. Okay, at the ends of beams and columns, and these locations where beam and column meets, these locations are called as beam column joint or beam column connections. So beam column connections would be subjected to bending moments due to earthquake loading. Okay, but the mid span and mid height, they are not subjected to any kind of bending moments. So bending moments will be produced at the beam column joints and ends of the columns, as you can see in this figure. So earthquake loading would cause bending moments at the beam column joints and ends of the columns, and these additional bending moments coming from the earthquake loading shall be added to the bending moments already produced due to gravity load, and then the bending moments, the flexural capacity by providing reinforcement shall be flexure capacity provided by reinforcement shall be provided against the combined bending moments from the gravity and earthquake loading. I hope this is clear to you. Okay, so as you can see from this figure, that the effects are produced at the beam column joints and at the ends. For this reason, the earthquake, whenever a frame structure is hit by an earthquake, then the connections of the frame system must be properly designed. Now, if the connections have been properly designed, it means that these connections would be capable of resisting bending moments, and bending moments produced due to earthquake loading. These bending moments at the connections which have been produced by earthquake loading are called as seismic moments. And you can see that seismic moments occur at the beam column connection and ends of the columns. So when we say that a frame is a moment resisting frame, by this we say that the frame is basically capable of resisting seismic moments. Okay. So one of our major objectives in the design of reinforced concrete frames is to design its connections. Beam column connections shall be designed such that they are capable of resisting these additional seismic moments produced due to earthquake or lateral loading. Correct? So the problem from all this discussion, what we conclude is that the problem in reinforced concrete frame structure design is what? The problem is the additional moments occurring at the beam column joints and at the ends of the columns, and this problem shall be resolved by enhancing the flexural capacity of the connections. In other words, these connections shall be efficiently designed, and they shall be capable of resisting the bending moments coming from the seismic actions. I hope this clarifies this concept. Okay, how shall this be done? This will be done by analyzing the frame for gravity load separately and then for lateral load separately, and then by combining these two actions at the specified locations according to the code combinations. And once the combined values are obtained, then the reinforcement shall be provided against all these combined bending moments in the same manner as we have done in the previous several lectures. Once you have bending moment, you will assume A and calculate AS. This time AS will be more at the connections, especially because the bending moment has been increased at that location. So AS, area of steel, will be more because there is a bending moments coming from earthquake loading as well. Okay, once this is done, the reinforcement is calculated. Over and above this design, there are some recommendations and provisions of the ACI code, and all these provisions and recommendation of the ACI code has one objective, and the objective is that the connections shall be efficient enough to dissipate all the energy imparted to the structure by earthquake action. So these connections must be properly detailed. Design, we have discussed that you have bending moments, you calculate AS and finish. You will provide the same reinforcement, flexure reinforcement. But the code wants to have some additional requirements in order to make these connections more efficient. And these requirements will be discussed now in the next slides. These are recommendations over and above our design requirements. And the principal goal of these provisions in the code is to ensure adequate toughness under inelastic displacement reversals brought on by earthquake loading. These provisions accomplish this goal by requiring the designer to provide for concrete confinement and inelastic rotational capacity. So these connections shall be confined enough using stirrups and ties so that to make them efficient with regard to the energy dissipation. Okay, and there are no special requirements on the frames which are located in low or no seismic risk. However, these requirements are placed only in reinforced concrete frames, which shall be constructed in the moderate or high seismic zones. Okay. If a frame is to be constructed, if a reinforced concrete frame is to be constructed in zone 2B, 3 or 4, so then the code says that in zone 3 and 4, not in zone 2B. If the code has basically divided reinforced concrete frames into 3 types, based on what? Based on their moment resisting capacity. When we say that the moment resisting capacity, by this we mean the moment resisting capacity of the connections of the beam column joints, because the earthquake loading will produce additional bending moments at the beam column joints, not at the midspan of the beams or columns. So when we say that the moment resisting capacity of a frame is good or bad, we mean to say that the moment resisting capacity of the beam column joints is good or bad. So if the beam, if the moment resisting capacity of the beam column joints is very, very good, then that type of frame is called as special moment resisting frame. So by this we can say that the moment resisting capacity of the connection of the frame structure, if it is very, very special, if it is very good, then that frame will be called as special moment resisting frame as per the ACI code terminology. If the capacity of the connections of a moment resisting frame is moderate, is not very good, so then it will be called as intermediate moment resisting frame. The words intermediate and special, they shall be referred to the bending moment capacity, special momentum capacity. So it is special frame. Intermediate means moderate type of efficient frame. OMRF is ordinary moment resisting frame. This frame has no special capacity. The connection, the beam column connections of this frame is no special capacity against the seismic loading. Okay, so now once these frames are known to us, then the ACI code has some more recommendations with regard to these 3 types of frame. The ACI code further says that special moment resisting frame must be provided in zone 3 and 4. In zone 3 and 4, the intermediate moment resisting frame and OMRF are not allowed to be used. In zone 3 and 4, if we are going to design and construct a reinforced concrete frame structure, this must fulfill, or this must be special moment resisting frame. This must fulfill the provision of special moment resisting frame. And in zone 2B, in zone 2A and 2B, special moment resisting frame is preferable, it is recommended, but IMRF is also allowed to be used. Intermediate moment resisting frame can be allowed, is allowed by the code. And in zone 1, SMRF and IMRF are both allowed, but if somebody wants to use IMRF or OMRF, then he's allowed to use in zone 1. OMRF is allowed in zone 1. Okay. Most of the time, even in zone 2A and 2B, we prefer using a special moment resisting frame because of its special capacity in energy dissipation. Okay, so once we decide in the beginning, if you remember last time we calculated the base shear, and in the equation of base shear, there was a factor called R, capital R, and that factor dependent on the that factor was dependent on the seismic behavior of the seismic anticipated behavior of the structure. So if the anticipated behavior of the structure is very good, by very good we mean that if the structure can go under several cycles of inelastic deformation without collapse, and all the damages occur at the control location so that life safety is ensured, then the R factor can be kept high. For special moment testing frame, the R factor is 8.5. As R factor is in denominator, so base shear will come out to be less when R is 8.5, and you will require less reinforcement as compared to another frame. For the IMRF, R factor is 5.5, and for OMRF it is 3.5. So when you say that I am going to construct my building in zone 2B, and if you want that this frame shall be SMRF, so R factor you will take 8.5 and base shear will be less. But when you do this in the beginning, because we in the analysis stage will decide whether I am going to design SMRF or IMRF, then at that stage the analysis parameter like R factor in the base shear will be considered, and the base shear will be calculated. From the base shear, forces will be calculated, and these forces will be then applied on the structure, and the analysis shall be completed with these forces, and the bending moments which are obtained from this later load analysis shall be added together to the gravity loading bending moments, and then the frame shall be designed. However, when we say that we will be designing and constructing SMRF, so this we say in the beginning, then the code has some special provisions for SMRF. As you will see in the coming slides, that these requirements or provisions of the code are very, very strict. And when we decide in the beginning that my frame will be SMRF and I will use R is equal to 8.5, so it is very obvious everybody would like to have SMRF in their frame structure design, because base shear will be coming less, and when base shear is less, bending moments will be less. However, in order to ensure that the frame is SMRF, the ACI code has put some restrictions over and above the design. Over and above, once you finish your design, then over and above your design, there are special provisions with respect to concrete strength, with respect to minimum reinforcement. At the ends are the beam column joints, with respect to the stirrups and ties. And you will see that the construction or detailing of the SMRF will become very, very difficult and demanding and challenging, because in the beginning we have taken an advantage of taking R is equal to 8.5 and thereby reducing your base shear. So once on one side, when you take this advantage by taking R very, very high, equal to 8.5, this is the highest value in the UBC, then the code wants to make sure that you produce the moment resisting frame, a special moment resisting frame. So on one side you are taking advantage, but on the other side the code has put restriction on the SMRF. So there will be finally a situation where a comparison between SMRF and IMRF can give you an idea which frame shall be selected basically in the zones where both of them are allowed. So with this discussion, now we will discuss further the ACI special provisions for seismic design. There are some provisions which are common to all the frames. For example, this provision of concrete strength of minimum 3000 psi is a general requirement for all types of frames. whether it is a special moment testing frame, IMRF or OMRF. The concrete strength in all parts of a moment resisting frame must be having a compressive cylinder strength of 3000 psi. There is no maximum limit on ordinary concrete. You can use as high as 15,000 psi concrete or 12,000 psi concrete if it is achievable at the site. However, if somebody wants to use lightweight concrete, then the maximum limit on the strength, compressive strength of lightweight concrete has been placed as 5,000 psi. And this is a little bit surprising, but this is because there is not enough data available on the behavior of high-strength lightweight concrete. On the reinforcement, if you want to use reinforcement in our frames, regardless of which type of the frame it is, then there are two options. If you want to use grade 60 steel conforming to ASTM A706, which is called as low alloy steel, then there are no further requirements of the steel. If you look at ASTM A706, this is a special low alloy steel, and this steel, the production of this steel in Pakistan is not very common. This was produced by some factories in the past only for some special purposes, like for their use in special structures such as nuclear power plants and other structures. However, some factories in Pakistan have now started their production very recently. This is a very good type of steel. It's a little bit expensive, but then it is very ductile because it is low alloy steel, and the strength does not. The strength is not coming from the carbon content, whether it is coming from some other from the addition of some other elements. So this is causing an alloy steel, low alloy steel, because it has very good properties. For further details, you can study ASTM A706. If we are using steel which conforms to ASTM A615, which is a billet steel and very common steel produced everywhere, all over the world, the most common steel type is the one which conforms to ASTM A615, and this is also called as billet steel. If we are using billet steel in our reinforced concrete frame members, and so it is allowed to use either grade 40 or 60, although the use of grade 40 has been decreasing day by day, because if we are using grade 40 steel, then the number of steel bars will be too many, and too many bars placement in frames, in frame members, beams and columns will be very, very difficult and demanding. It will require large sections of frames and members, large section of frame members. So for this reason, now we prefer using grade 60. Recently, some factories in Pakistan have also started producing grade 70 steel. we have used in one of our recent projects on the University Road in a project called as Diamond Mall here, close to the Abdara Road. This is a 15-story high-rise building where we recommended the use of grade 70 steel. Okay, so if we are using grade 40 or 60 steel, then there are two further requirements of the code, that the yield and the actual yield and the specified yield, the difference in actual yield and the specified yield shall not be more than 18 KSI. Which means that if you test a steel bar collected from your steel located at the site, and it comes out to be, let's say, 70 KSI, and it is grade 60 steel. So the specified steel, the specified is the one which you specify. This is 60 steel, 60. So actual you can only obtain from test in the lab. So if you test a reinforcing bar in the lab, and the bar is grade 60, and the actual yield comes out to be 70, so it will be 70 minus 60 equal to 10. This is good, this is allowed, because 10 is less than 18 KSI. However, if you obtain the yield of 90 KSI, 90 minus 60 is 30, and 30 is more than 18, so it is not allowed. Which means that the difference between the yield, actual yield, and the specified yield shall not be more than 18 KSI. And this, by this requirement, the ACI code wants to make sure that the gap between the yield and ultimate, a minimum gap between the yield and ultimate, is kept. So if yield is very, very high, it is quite possible that yield is very, very close to the ultimate, and the reserve energy that we consider in our designs, by not taking strength more than the yield in our designs, will be compromised. So this is not a desirable situation. Now, the other requirement of the code is that actual ultimate divided by actual yield shall be more than 1.25. So by this, we mean to say that actual ultimate, if you test a steel bar of grade 60 grade 60 steel, you test in the lab, and the ultimate strength of the bar comes out to be, let's say, 90 KSI, and the actual yield comes out to be, let's say, 65. So 90 divided by 65. If 90 divided by 65 is more than 1.25, then it is okay. If it is less, it is not okay. 90 divided by 65 is 1.38. 1.38 is greater than 1.25, so this is okay. However, if actual ultimate coming from the test is 80, and your actual yield is 65, so this is 1.23. 1.23 is less than 1.2, this is not good. By these two provisions, the code wants to make sure that the gap, there must be some minimum gap between the actual ultimate and actual yield, so that the ductility is achieved. The ductile behavior of the steel, as you know very well now, that the ductile behavior of the steel starts exhibiting after the yield. So if after the yield, the gap between the yield and ultimate is very narrow, then the ductility of the steel will be less, because by the definition of ductility, the ductility is basically defined as the deformation ductility. The deformation ductility or strain ductility is defined as strain at ultimate divided by strain at yield. So if the gap between these two, ultimate and yield, are very narrow, then the ductility will be less. And the ACI code wants to make sure that ductile bars are used in frame structures. Okay, some general requirements on the hoops and ties. The confinement for concrete at the connection is provided by transverse reinforcement consisting of stirrups, hoops, and cross ties. This is a seismic hook. This is a seismic hook provided in a stirrup. This stirrup is called as open stirrup. This is an open stirrup. Okay, stirrup, open stirrup. This is called a cross tie consisting of one single bar with a 90-degree hook on one side and 135-degree hook on the other side. Okay, if this cross tie is placed on top of this stirrup in this manner, then it is called as a stirrup plus cross tie. It is being closed. The stirrup has been closed by this cross tie. But this closing of the stirrup has occurred due to the placement of cross tie. Okay, stirrup plus cross tie. And when this closing of the stirrup does not occur due to the cross tie, but rather it occurs due to the closing of the stirrup itself, by starting from one point and then completing the full cycle, coming out and then ending here again. So this stirrup is being closed by one single bar. This is called as continuous tie. Continuous tie are, but both of these are also called as hoop. When stirrup is closed, it will be called as hoop, regardless of the closing, whether the closing has occurred due to the cross tie or if it has occurred due to the use of single bar. Okay, this is called as continuous ties, and this is called stirrup plus cross tie. Both of them are called as hoop. This is a cross tie and this is a stirrup. These are used in the for the confinement of connections. You have used them for shear reinforcement, if you remember, in your beams. Okay, a seismic hook is a hook which is the turning around of the ends and start of the bars at an angle of 135-degree. And the reason for this is when they are turned around to the internal side of the tie. So you know that there will be concrete here, and there will be some connection made between this extended length of the seismic hook to the concrete. So it will become now difficult in an earthquake event. So the opening up of this cross tie will become very difficult in earthquake event because of this connection between the steel bar and the concrete embedded here, and the concrete in the concrete the embedment provided by concrete, these parts. Okay. The closely spaced horizontal closed tie in column help in three ways. They carry the horizontal shear forces, you know this, induced by earthquakes and thereby resistant diagonal shear quakes. They hold together the vertical bar and prevent them from excessively bending outwards. In technical terms, this bending phenomena is called buckling. But this is not the buckling of the whole element, as you been aware of buckling phenomena in the case of long columns. By this buckling, we mean only the buckling of reinforcing bars. Okay, and this can occur at the final collapse stage when concrete cracks extensively. Then the bond between steel and concrete will no more exist, and in this situation, the steel will be alone against the gravity load. So under this situation, the buckling of steel can occur. But then, if closed ties have been provided all around these bars, then they will prevent such type of buckling at the collapse stage. They also, the steel bars, the strips and the ties are provided to contain concrete. Usually, though from the shape point of view, there is no difference in strip and tie, but it is a traditionally it is a practice that whenever this kind of bar is provided in beams, it is called a stirrup, and if the same is provided in column, it is called a tie, although there is no difference in their shape. Okay. Now, provisions for flexure members in SMRF. These were general provisions up to from the slide number 61, 62, 63, 64. These were the general provision for all types of reinforced concrete moment testing frames. But now, specifically for special moment testing frame, we will study these requirements one by one. First of all, we will study the requirements of flexure members in the beams. But before we start this, I think we should take a break now. I will join you again after 15 to 20 minutes. I have a small meeting, so I will attend the meeting, and you can study these slides. If you have any question after the break, we will continue, and I will try to answer your questions. These provisions are for flexure members, for beams, and then for columns. Okay, for special moment testing frame, and then we have provisions for intermediate moment testing frame, and finally there is an example how to incorporate all these provisions in a practical frame. What's yours? Okay, so we will start from slide 65. I apologize for being late because the meeting which I was attending took longer than the anticipated time. So I had to be there. This was a signing ceremony between UAT and UNHCR. Okay, the meeting ended just right now, and we will quickly go through a few of these slides, and we'll try to complete this lecture in the next week. Okay, if you have questions, you can come up with your questions next time. We were talking before the break that there are some general provisions for movement testing frames, and then there are specific provisions of the ACI code for the different types of movement testing frame. These provisions which we are discussing right now, they are related to spatial movement testing frames. And within the provisions, then they have been subdivided into flexural members, which are primarily beams, and also to compression members, and to compression members, which are primarily columns. And then there are provisions for the beam column connections and joints. Okay, so first of all, we will study the provisions for flexural members, which means beams. These provisions apply to flexural members, and the criteria for a member to be categorized as flexural member is that when the factored axial compressive force from the analysis is less than the 10% of the axial capacity, which is AG times FC prime. You know, this will give you the load carrying capacity of the column. When you multiply gross area with the compressive strength of the column, this will give you the axial load carrying capacity of the column. And when this is divided by 10, which is 10% of this capacity. So if the compressive force coming from the analysis is less than the 10% of the capacity in axial load and axial capacity of the column, then this will be treated as flexure. Why has this criteria been established by the ACI code? Because you know that beams primarily, they do not take any axial load in the frame structure. So this axial load on the beams is generally less than the 10% axial load capacity of the column. So when the situation is like this, so that will be treated as flexure member. However, sometimes there may be columns in low-rise structures, especially where the load on columns is coming from lightweight steel trusses. In that situation, even a column can be subjected to axial compressive load from the analysis, which comes from the analysis, can be less than the 10% axial load carrying capacity of the columns. So for those columns, also these provisions apply. Okay, and these provisions are: number one, on the size of the member, that clear span to effective depth ratio of at least 4 shall be maintained. What does it mean? It means that if length of the beam is, let's say, 15 feet, if length of the beam is 15 feet and the effective depth of the beam is 16 inch, then L by D ratio, 15 divided by 16, 15 into 12 to convert this into inches divided by 15 is 11.25. So L by D ratio is greater than 4 because 11.25 is greater than 4. However, if there is a beam, a very short span beam, let's say 5 feet beam, if there is a 5 feet beam, very long, very short span beam, and if the beam depth is say 2 feet, so 5 divided by 2 will be 2.5, and 2.5 will be less than 4. So that condition shall be avoided, because if beam is very short span and the ratio of length to depth of the beam is less than 4, then such beams will fail primarily due to shear stresses instead of flexural stresses. And you know that flexural cracking and flexural stresses, the failure due to flexural stresses and flexural cracks is more desirable than the shear failure. So for this reason, we would like that beams which are part of spatial movement testing frame shall fail in a flexure mode instead of a shear mode. Okay. So a width to depth, and then the second provision on the side is a width to depth ratio of at least 0.3. The width of the beam to depth ratio shall be greater than 0.3. For this, the example is, let's say the beam is 12-inch wide and it is 18-inch deep, then 12 by 18 is 0.67, and 0.67 is greater than 0.3. You know this very well. However, if beam width is 12-inch and depth is, let's say, 60-inch, so then 12 divided by 60 is 12 divided by 60 is equal to 0.2, and 0.2 is less than 0.3. So for this reason, that condition is not allowed. This condition has been placed in order to avoid some kind of slenderness in the beam with respect to depth of the beam, not with respect to the length of the beam, but with respect to the depth of the beam. If beam width is too small, and if it is too deep, then along the depth of the beam there will be some kind of slenderness which need to be avoided. The third and the last provision with respect to size of the beam is that beam must be having a width of at least 10 inches. 10 inches, width less than 10 inches is not in the beams which is part of testing frame. And the flexure reinforcement. And the flexure reinforcement. On the flexure reinforcement, as we have seen in the beginning of our today's lecture, that all actions in the reinforced concrete frame occur at the ends of the beams or at the beam column joints. So you have seen that additional beam column joints, the flexure reinforcement, longitudinal reinforcement must be up to must be certain limits which have been defined by the ACI code. And these limits are, as mentioned in this code, the minimum reinforcement ratio. You know this very well. This should be maintained at all critical section. The maximum ratio is being fixed at 0.25, and there is a requirement that minimum 2 bars shall be continuous at all sections. And this we know, even without the seismic provisions, we always keep minimum 2 bars in top and bottom portion of the beam. Beam is part of if a beam is part of special element testing frame, then at the bottom side, on the bottom side of the beam, a beam column joint, the minimum reinforcement shall be at least 50% of the top negative reinforcement at the beam column joint. Okay, I will try to explain this once again. This is a beam column joint, and this is the top portion of the beam. You know that negative reinforcement is placed in this region. And in the case of special element testing frame subjected to earthquake forces, this ASL negative, AS means AS and L means left side. AS, area of steel on the left side, and this is negative reinforcement, so this negative sign is being mentioned. So this reinforcement will come from where? This reinforcement will come from the combined action of combined bending moment of gravity and seismic loading. Once this reinforcement is calculated from the bending moment, okay, then this reinforcement will be known to us. A reinforcement, and then from the analysis obtained from the analysis is less than 25% or 50% of this, then this reinforcement on the bottom side of the beam shall be increased up to a level where this is at least 50% of this reinforcement. An example, we have we have 8 bars, 8 bars, 8 bars, let's say, a stop negative reinforcement against the bending moment, which is obtained from the analysis due to the combined action of gravity load and seismic loading. So if we obtain 8 bars here on the top side, and from the bending moments which is obtained from the analysis of the gravity load as well as the lateral load, the reinforcement comes out to be, let's say, 3 bars. So from the design, the reinforcing bars are 3. Okay, yes, the bottom bars, and from the design calculations, top bars are, let's say, 8 bars. So these 3 bars are not 50% of the 8 bars. So according to this criteria of ACI code, 1 bar shall be added to this, although the calculated bars are 3 from the design. Okay, so 1 bar shall be added to this to make this connection efficient, and this connection will only become efficient, and you can call this as a beam of spatial moment testing frame if this criteria is fulfilled. If this criteria is not fulfilled, then the initial assumption while we were calculating the base shear, and where we took R is equal to 8.5, will not be correct, because R is equal to 8.5 will be correct only and only if all these provisions of spatial moment testing frame are fulfilled. Only then you can take R is equal to 8.5, because R is equal to 8.5 will reduce your base shear, and this reduction of the base shear is only allowed if you make all these parts which are subjected to earthquake loading, especially the connections of beams and columns. If you make these more efficient, and you can make them more efficient so that they dissipate energy by fulfilling all these provisions of the ACI code. So one of these provisions is the previous provision was with regard to size of the beam. This provision is with regard to the flexural longitudinal reinforcement. Longitudinal reinforcement at the beam column joints in the beam on the bottom side of the beam shall be at least 50% of the negative reinforcement. Okay. At any other location, there is another requirement that A is negative or A is positive at all sections. At all sections means here at the top part of the beam, mid span top, bottom span, mid span bottom. Okay, in any location of the beam. At any other location of the beam, the reinforcing bars shall be at least 25% of the maximum area of steel at either joint. So in the previous example, which we were talking about, location in this beam, 8 divided by 4, at least 2 bars shall run in every part of the beam. And if these bars were 12, then 3 bars shall run everywhere in the beam, as top reinforcement as well as bottom reinforcement at all sections, whether it is mid span or end sections. End sections or mid sections, everywhere 25% of the maximum reinforcement shall be provided. Okay, this is another requirement. Transverse reinforcement. Transverse reinforcement means the stirrup reinforcement. Whatever stirrups are being calculated from the design, they shall be finally checked with this provision. And this provision says that within the region from the face of the column into the beam equal to twice the depth of the beam. In this location, on both sides, the spacing of the stirrup shall be kept equal to D by 4, 8 into smallest longitudinal bar, 24 into hoop bar diameter, and 12 inch. It should be least of this. An example to this will be, for example, let's say the depth of the beam is, let's say, 2 feet. So this region will be 2 multiplied by 2, 4 feet on this side and 4 feet on this side. Within this location, the spacing of the stirrup shall be equal to D by 4. Let's say if it is 2 feet, as I said earlier, it will be 24. 24 inch divided by 4, 6 inch, or 8 into smallest longitudinal bar diameter. And if the bar diameter is, let's say, 6 by 8, so it will be 8 into 6 by 8, so it will also give a 6-inch strip. Diameter is 3 by 8, so 3 by 8, 8 into 3, and 3 multiplied by 3 will be 9 inch. So 6, 9, and 12 inch. And the least of this is 6 inch, so we will select 6 inch. Okay, like this. So the spacing shall be kept, no matter what is the spacing coming from the design. And elsewhere, you can keep the minimum spacing good by 2. Lap splices, lapping of this critical region, which is at 2H from the face of the column, and also they shall be kept away from the midspan. This is the lapping of the bottom bars. The lapping of the bottom bars shall be widened at the midspan of the beam, and ends of the beams in the critical region extended from the face of the column into the beam equal to twice the depth of the beam. So all the yellow locations, the lapping shall be avoided. The bottom bar shall not be lapped in the location shown here in the bottom bars or the bottom bars, not at the midspan, not at the end of the beams. And the negative bars can be lapped at the midspan because there is no negative bending moment here. And however, they shall be avoided to be left at the end of the beam in the critical region. Okay, so lapping shall be avoided. The basic principle is that lapping shall be not allowed in the regions where longitudinal bars can yield in tension. Mechanical splicing is allowed. Mechanical splicing means if splicing is not done through lapping of bars, and if it is required to be spliced through some mechanical arrangement, then even then this criteria shall be fulfilled, that mechanical splicing will be allowed in those locations where lap splice is allowed. However, there is another requirement for mechanical splicing, that a full mechanical splice shall develop in tension and compression is required at least 125% of the specified yield strength of the bar. Mechanical splicing, is obtained through certain arrangements. You have studied this in the lap splice lecture, where mechanical splicing was also discussed. Okay, so what mechanical splicing arrangement is used, that the mechanical splice arrangement shall have a strength of at least 125% of the yield strength, so that no breakage of the mechanical splice occurs at the locations where the splice is being provided, and that it is to make sure that yielding occurs at that location instead of breaking a part of the mechanical splice arrangement. Similarly, welding is also allowed, but the welding is allowed in all those locations where lap splice is allowed. And the criteria, again, for the welded splice, the strength of the welded splice shall be at least 125% of the yield strength of the bar. So I think this is enough for today, and the next time we will try to study the remaining part of this lecture. The next provisions are with regard to the columns. So we have covered today the special moment testing frame, special provisions for beams. Next time we will try to complete this lecture with the remaining slides. Thank you very much, and I apologize once again for being late because of the very important meeting. I hope you are able to understand what we have studied today, and if it is not clear and you have questions in your mind, you can ask questions today or in the next lecture. Thank you very much. Okay, any questions?
No, sir.
Okay. Thank you very much.